this notebook, I will talk about distance metrics first. Very important thing. I always want to go from you guys to know what's the idea of using distance metrics in machine learning. Let me see your answer. So I have some motivation. You have some motivation. Anyone know the use case of machine learning? Oh, sorry, use case of distance metrics in machine learning in clustering of. Wait, think it, dive into it, Michelle. Sorry, I always pronounce your name Michelle, but am I correct? Because I think Michelle sometimes is a female. Sorry.
Yeah. It's actually, can you hear me?
Yeah.
You're right. It's pronounced Mitchell, but I quite often get Michelle from
Michelle.
from a lot of people, really.
Yeah, Michelle, you are correct. You don't need to mute yourself. I just, if you dive into it, you determine the distance between data points. So what's the next step? What's the benefits of that? For clustering or for other use cases?
Yeah, I think it's just to try to identify the cluster by identify the point close to each other.
Yeah.
So intra distance to be minimum and inter distance between other clusters as well as a gap as much as we can. So then we can say all of that's one cluster, another cluster as well is quite separate based on distance.
But yeah, that makes sense. What you said is, okay, I want to do the clustering. How I can do the clustering is determined by how close or how far away from the data points from each other's, right?
Yeah, that's right. And as you know, there is centroid as well, just to define a center.
Yeah. That's great. You identify centroids as kind of reference point to determine the clusters.
Yeah.
Thank you for bringing that. So now everything become more concrete. I mean, more concrete is like if you don't use centroid, I will ask you, okay, now you know the distance between each pair of the data points, but how it can only give you general sense of, okay, these two data points is closer than other two data points. Let's say A and B is closer than A and C, so it's more likely I will put A and B together. But then you need to compare of each pairs of data points. You compare A and B, A and C, A and D. It will be you can do clustering in that way, but it will be very, very brute force, not inefficient. So Amma just said, okay, I have a centroid ideas. I can use the centroid as reference point. You don't need to calculate each pairs of data points. You can calculate all the distance between the centroids, maybe two centroids of three centroids, determines how many numbers of clusters you want. So you only need to calculate the distance between centroid and all other data points. Then if centroid A is closer to data point B, you will make compared to centroid C and D, you will make data point B into cluster A, into centroid A, because each centroid represents one cluster. Sorry, so that will be more efficient. Thank you for that. So now I talk about the general idea of K-means, but I will show you the details, so no worries. See how close the points are to each other within the same cluster. Oh, that's really great. Margaret, why we need to see that? It's for modeling, or it's for evaluation, or for any other things you think about?
I think for both, in my opinion, because when you group, like clustering is like grouping, right? Subgrouping. So you want to make sure that they are very close to each other so that you know that they actually belong to the same species or same group or same cluster, whereas like the distance between different clusters should be as far as possible so that they could be distinguished, like, or they could be separated. So that is the idea in my head, like why we need to measure the distance between points.
Yeah, yeah, I think, yeah, Margaret is very, very correct. He said, okay, I want to measure how close the points are to each other within same clusters. In KMeans, you will do that. Actually, KMeans has actually 3 steps. One step is initialize the centroids. Another step is assign the different data point to this centroids, initialize centroids. Then you, according to this assignment, you update the centroid. So 3 steps: initialization, assignment, and update. So how close the points are to each other within the same clusters? It's kind of related to the update step. Once you do assignment, you will update the centroid. In that case, actually, you will it's kind of look at, okay, how it's measure, yeah, how close the points not are to each other, but how close the points to the centroids within the same clusters. But I think your idea of how close the points are to each other can also be used for modeling, just like the brute force idea you just, but still, we need to have a further thinking how we can use these points to each other within the same cluster to make a clustering algorithm. It's beyond the scope of what we will talk about today. But as regarding evaluation, the Margaret idea is exactly what we'll talk about today, how close the points are to each other within the same cluster. I think this will be calculated in, I think it's called silhouette score. Yeah, we will look at later. So then we will go back to see whether the Margaret, this idea is related to the evaluation metric. I just copy paste of Margaret's what Margaret said, so we will see it later. Here is the evaluation phrase. Yeah, I will copy paste it here. So we'll go back to this. It will be interesting, right? To get inter-class distance and intra-distance between data points and between cluster. Yeah, I won't ask your question, Akin, but thank you for bringing that. This is related to Margaret's idea. So intra-distance, I think the intra-distance, what do you mean the intra-distance is exactly what Margaret said. Then you said get inter-distance. That means you calculate the distance between one data point in cluster A and with other points in cluster B. So they are in the different cluster. This is also directly related to the calculation of silhouette score. So let me also copy paste this one. So yeah, I think since I'm a researcher, I always like to copy paste and give a name who say that. You know, this is credit I should give to you guys. Akin. Okay, great. So that is the purpose of distance metric. Now you have the motivation, right? It's very, very important for clustering. I think there are a lot of use case, but okay, it's enough. Now my question is, what's the distance matrix you know? What are distance metrics you know? Can you give me answers, indication? You know, I really hate this, always appear. How I can close this forever? Euclidean, great. Actually, that's the first one I want to begin with. Great, great. Always from Euclidean, right? That's one's most close. I think it's most close to our real life. Not most close to our real life. You mean you go to let's say you go from Burwood. You know, Deacon is located at Burwood to Caulfield. My home is located at Caulfield, so I always need to drive from Burwood to Caulfield. So what's the distance between Burwood and Caulfield? Oh, Manhattan distance. Yeah, actually sometimes it's more like Manhattan distance because there is no direct point from Burwood to Caulfield because there are a lot of block, right? I can't go via a line. So Manhattan distance. Anyone has gone to Manhattan before? I mean, in New York. Just give me a thumb up. Actually, I've been there. It's very interesting. You know, it's very vibrant city. Not like Melbourne. You know, every shopping center will close. Only some bars will open in central. Yeah. By the way. Okay, great. Michelle, you went there. Michelle, Michelle, can you just describe when you look at? I think you use Google Map in New York, right?
Yeah.
Have you saw that the street maps of in New York is very it's very weird. It's very. Do you notice that?
It was like a lot of blocks.
Yeah, a
Like,
lot
very,
of blocks.
yeah.
You have vertical line, you know, it's a horizontal line and vertical lines. They are horizontal to each other. It's like grid.
Yeah.
Melbourne it's not. You know, in Melbourne Central, you have Swanton Street, you have Elizabeth Street, you have King Street, you have William Street, then you have Collins Street on horizontal and Little Collins Street on horizontal. Yeah, it's like blocks. But when you go up, you go to the north, you will go like Victoria Lane, Victoria Road, or Victoria Street. I'm not sure which one, but the road name is called Victoria. It's like, you know, a triangle. It's not like a completely horizontal to each other. So, but in Manhattan, they are very strictly horizontal to each other and align, you know, parallel to each other or horizontal line or vertical line. So that's why I said that's very unique, interesting thing. Yeah. Okay. So cosine distance, great. So who sets cosine? Okay, Amma said cosine distance. Amma, I can ask the question. Do you know when should we use Euclidean distance? When should we choose cosine rather than Euclidean distance?
If I got it right, the Euclidean is just like direct line between A and B. But the cosine, if we care about the direction and angle, so we think about cosine.
Yeah, so I want to make it more concrete. I think all of you know angle and all of you know line, so it's easy for you. But I just want to give you real use cases. Sorry, this is my research project. Okay, another research project. So I have
Is it just me? We can't hear you.
opposite.
No, same for me here as well. There is like a bit of delay or cutting off.
The second column is the appearance of these words in document. Sorry.
I'm sorry, you're cutting out. We can't hear you properly.
Wait, let me fix this problem. Can you hear me now?
Yep.
Yes.
Yep.
Oh, sorry. It's because AirPod. You know, once I touch the AirPod, it is activated. So I just wear this AirPod. Okay, so I will go back to these examples. So for clarifying the Euclidean distance and cosine distance, this example is for natural language processing domain. You know, in language processing domain, we begin from words. So we have 3 words here. It's very simple: superb, good, and bad. We want to calculate the similarity between these words. You can see super and good have a very similar semantics. So they should be, you know, the distance should be very, very small compared to the distance between good and bad, right? I think this is very easy to understand, right? Okay, so I just go forward. Just interrupt me if you can't understand what I say. So because sometimes I don't clarify it in a simple way. Yeah. So how I can represent these 3 words? I use the frequency of these words appearing in documents. That's in real life how we represent these words. For example, this first column is for document A. It will record how many times super appear in document A. You see, super appear in document A twice, in document B 4 times, and super appear in document A 10 times, in document B 15 times, same thing, 14 and 10 times. So actually now you can make a very, very simple assumption here. You can see the document A is about is a negative review. It's a document B is more like a positive review. I think it should make sense for you. Just look at how this data, how this value are specified for each words and each documents. You can see here there is 2, there is 4, so always smaller than document B for super words. For good words, you know, for good words the same, right? Always smaller than document B. So it's more like you can see the last example. For negative words is more frequent than the for this bad word in document B. So it's B negative. Vice versa, you can compare. Any problems so far? Nope. Okay. Hopefully you understand this example. So then you will have a very intuitive understanding rather than very high level understanding. I need to turn on the light. Okay, now let me plot this. You can see this is where the super stand for. This is where the good stand. This is where the bad word stand. Let's see. Now you calculate Euclidean distance. It's just a line, right? Super to good is apparently longer than good from good to bad, right? Okay, if you understand this, I will ask you why it happens in that way. Why super and good, the distance, Euclidean distance between super and good is larger than good and bad. Any guess for this problem? You know how we make this representation makes sense, right? Super is positive word, so relatively in positive document is more likely appear in positive document compared to negative. Same for good, and bad is a negative word, so it's relatively is more possible appear in the negative document compared to positive document, right? So everything makes sense, but why the Euclidean distance between super and good is larger than good and bad? Let me see. No answer. Okay, I just wait for 30 seconds so you can have a think. Oh, great. Can I ask you how I can pronounce your name, Simone?
It's fine, yeah, it's Simone, but it's however you say it is fine. I get all sorts.
Yeah, sorry, Samai. Samai, when you say it, what do you mean? It means which word appear less often? Superb. Yeah, correct. The thing is because, you know, good and bad are very, very popular words used in our daily life. But super is not that common compared to good and bad. So now make it more general. It is because the magnitude, right? So in this case, if you want to compare the distance, what actually, I don't want to ask the question because someone already gave me the answer. You can use the angles, right? If you calculate the angles, sorry, I should have a graph here. Let me plot a graph. If you calculate the angle between super and good, you know, this angle is very small. Oh, that means they are close to each other. And the angle between super and bad is very large. So they are further away from each other compared to super and good. So that's why we need to use cosine similarity. It is we use that when the magnitude will stop us to find the true semantics of this representation. Yep. By the way, for this, anyone know why the calculation of cosine similarity will avoid this issue? Why the cosine similarity will avoid the issue of magnitude?
Is it because it's looking at the angle and not the distance?
Yeah, actually, you know, you are correct. One thing I just want to clarify: the cosine similarity is not the angle, but the distance but the similarity align with cosine similarity. Be careful, cosine similarity, not cosine distance. Cosine similarity align with the angle. If the angle is small, the similarity is small. The angle is big, the similarity is big. Oh, I confused myself. Sorry, let me re-clarify it again. If the angle is small, that means the similarity is big. Small similarity big, but the cosine distance is small. Okay, so cosine distance align with the angle. Yes, that is one clarification. Just go back to what Michelle says. Michelle says because we look at the angle, not the line. Correct, but what I want to point out is how you calculate these cosine similarities. Get rid of angle. I bring out the concept of angle just for you to have an intuitive understanding. But that's not how we calculate cosine similarity or cosine distance. Anyone know how we compute cosine distance or cosine similarity? Once we compute cosine similarity, what we do is 1 minus cosine similarity. That will be the cosine distance. Anyone know how we calculate the cosine similarity? I just give you 15 seconds to maybe you can go through Google, you can search for it, look at wiki. I think it's always better to let you talk about the answer rather than I give you the answer. Yeah. You can see Margaret just sent equation. Margaret, do you understand how this equation works? There is there is symbols, the operation between x and y. What's this operation?
Dot product of matrix X and Y, and
Yeah.
then divide by the square root of this one should be dot matrix of X and X itself, and then
Yeah.
the other guy is square root of the dot product of matrix Y and matrix Y itself. Yeah.
I just want to give you guys a more intuitive understanding of this equation. In this x dot product y, you are correct, it's dot product. X and y is a vector. I don't like to use the word matrix because here is just one dot point, so it should be a vector. Take the example here. I have super and I have good. So how I can calculate the the dot product of super and good? What I do is I take a first row is this, right? Then I do the dot product. I don't use this. I just use the dot. You see, this is a dot product between good and super, right? I always want to show you the result. This is super and good. What's the result for that? It's 18. So let's look at the dot product between super. I don't want to look super and bad. I want to look at good and bad. So let me print the result for you. Let's say if the dot product itself can work as a good distance matrix in this scenario, then you see, still super and good, good, super and you, super and good have this is similarity. Okay, don't be confused. Here we use dot product to calculate the similarity. Okay, dot product, one is bigger. It looks like if we calculate similarities, it's bad between good. It's not. It shouldn't be. Oh yeah, it's correct. This is bigger. So the good and bad has a bigger similarity here. You can see. So it's not make sense, right? Distance, because I don't want you confused. Similarity in this case is equal to 1 minus distance, but the distance, I shouldn't say this way. I should say the distance equal to 1 minus similarities. But only I can use this equation. Only the similarity is normalized. That means the similarity is between 0 and 1. So for this case, what you need to remember is, okay, the distance is opposite to the similarity. That's enough. So I just get rid of this. So, okay, so you can say it's not reasonable, right? The good and bad have a larger similarity. Nope, shouldn't be the case. More intuitive understanding is if you, in your high school, I'm not sure in Australia, in your high school, do you learn some geometric understanding of dot product? In China, when my teacher taught me the dot product, it will give me this intuitive geometric understanding. Dot product between good and bad is equal to the length of the good vector, is this line, multiplied by the projections of bad onto the good. The projection and bad onto good is this line. And the super projection of super to good is this line. So the first multiplier is same, is this length, right? But the second multiplier for bad is this length. For super is this small length. So intuitively, the similarity between super and good is always smaller than bad and good. So it's not what we want. So why is that case? It's because magnitude, again, the magnitude is a problem. You see, the magnitude of this line is bigger than this line, bigger than this vector. So what we can do is, okay, I just divide it by the magnitudes. How we can calculate the magnitudes of vector? We use norm. We use AP dot L. Sorry. Then we can use, why there is some, then we can give this vector, then we can also take the norm of the second vector. So then we divide it by this norm. So this is normalization, right? It's similar to what we learned last week about the min-max scale. So min-max scale is a normalization technique for features. So here is also normalization techniques. Now you can see the results. The similarity between, oh, no, it's not, it should be 1, right? Then it should be 2. Here is 1, 0, 1, 0, 1, super good. Here is 1, 2, 1, 2, good, bad. Now we can see the result. Great. It's now the similarity between super and good is much larger than good and bad. So, but what we want is distance, right? So just 1 minus. So now it's not similarity, it's distance. Great. You see the distance between super and good is much less than the good and bad, right? Makes sense, right? That's one use case I want to show you in my domain to understand when we should use cosine similarity, when we should use Euclidean distance. Hopefully it will be interesting. Any question for this? What do Don't we use the transpose? Yeah, we can use the transpose to calculate the dot product. Actually, the things we use transpose is just we follow some linear algebra practice, but it's not intuitive, so I will avoid that to calculate the dot product in this unit. But in my own project, I prefer to use transpose because it's very concise. Any other question? Nope. So if no question for Euclidean distance and cosine distance or cosine similarity, I just want to hear more distance metrics from you. Just for interest, I don't think you will use other distance metrics in this unit. Maybe, I'm not sure, but any idea for other distance metrics? We talk about Euclidean, Manhattan, and cosine. How about I give you one use case also in my, normally in my domain, there is use case like, okay, we have words, right? We have something like, don't talk about words, just talk about sentence. We have different sentence. Let's say I am good. So we have a tokenization phrase. Once we want the machine learning model to learn this sentence, you already gave the answers. I haven't give the question yet. But never mind. I just gave the use case for Jacquard distance. Actually, this is one use case for Jacquard distance. We have a sentence, right? I am good. So we need to tokenize it. This is what's tokenization? Tokenization means I make a sentence to different tokens. Normally, tokens just means words, but sometimes we use characters. Sometimes we use subwords. Subwords is like, okay, good becomes CO and OD. Yeah, here is the tokenization. I tokenize this into I am good. Now another tokenization is I'm bad. So here I just copy paste this. Oh, I shouldn't use this curly bracket. Actually, I should use this. Oh, I shouldn't use square bracket. I should use curly bracket. Anyone know what's the difference between curly bracket and square bracket in Python? How about this? Is this dictionary? What? Nope, it's not dictionary. It's set. I see Daniel says the Jacquard distance for similarity of sets. In Python, this is set. Actually, normally in mathematical notation, we also use this curly bracket for set. But you are right. Curly bracket is also reserved for dictionary. But we have a key and we have value. Then we have this column. I think this semicolon, right? Then we have another key and another value. This is a dictionary, okay? But this is set. So in this scenario, I want to calculate the distance between these two sentences. Normally, Jacquard distance will do the what? What Jacquard distance will do is, if someone knows Jacquard distance, can you directly give me answer? If I use Jacquard distance, what's the answer will be for distance between these two sentences? I give you 15 minutes. Let's see 15 seconds. Let's see if we have answer. I think I will run out of time, so I just give you answer. For Jacquard distance, we will have a nominator and denominator. The nominator is the intersect of the sets. Intersect is a common element. Here we have common element, two common elements, I, N. So this is the intersect. I will calculate the size of this intersect. And the nominator is size of the union. Union is all the elements appears. No duplication, right? IM already appears in this union, so I don't put it there. So this is a Jakarta. Actually, this is Jakarta similarity. I need to 1 minus this. So we have a Jakarta distance. Okay. So this is a 2. This is 1, 2, 3, 4. Oh, sorry, it should be byte rather than here should be byte, not good. So it should be 1 minus 2 over 4. So it's also 1 over 2. This is Jakarta distance. Okay. So that's it. I don't think that's I want to talk about more about this distance matrix is enough. Now I will go to the K-means. For K-means, we need to use distance matrix to calculate the distance between the centroid and the dot points. I just let you see that again to connect the two topics. But normally you won't see how this code is run. I will show you the detailed code how we can implement this process in Python, pure Python. Don't use sklearn API. But firstly, let's use sklearn API. I think all of you know how to use sklearn API. It's very easy. You import the name of the algorithm. Here it's called KMeans. You define it. You give some hyperparameters. Hyperparameters means that the things you need to determine before you train these models on the data. So you predetermine this hyperparameter. Here, the hyperparameter is number of clusters. Note that not all clustering algorithms require these hyperparameters. For example, dbScan doesn't require this hyperparameter. It don't need to know how many clusters you need for training a dbScan model. So okay, so you define it. Then all the things are same. Supervised learning models, linear regression, logistic regression, neural network, all of them just use same method. You call fit, then you call predict. Hold down. You call fit, train on this data. Okay. In supervised learning, you have a label, so you need to write y, but it's clustering, so you only need to provide x. So you do the prediction. All good. Not very interesting. So, but for your assignment, you can use sklearn API. Here is one example. The example is about the height and weight of persons. Actually, I gave you label here, but in clustering we don't have label. But in some case, we have some intuitive before doing clustering. We have some intuitive understanding of data, so we can have a hypothesis like, okay, I thought once we do the clustering, actually don't think about clustering so far. Before doing clustering, I have a hypothesis that this data is mostly it can be grouped according to the one feature, according to the adult and baby. If it's adult, this description of this person will be in one group, one subgroup. If the example is baby, this example will be in another subgroup. This is our hypothesis. So using this hypothesis, you have some kind of this, look like labels. But you shouldn't care about this. You want to do clustering. After you do clustering, you have a look at the prediction. You see, whoa, the idle always be clusters together, right? And the baby, the second example, third example, first example, oh, they are also clustered together, group as one cluster. So my hypothesis is correct. So now I know something about the data, and I use clustering algorithm to prove that. That's the use case, right? Before I go into the detail of K-means, I want to know, now I have the model, how I can evaluate the model. If I let you to evaluate this model, okay, I got the answer, but I don't know if this answer is good or not. What should I do? Adding evaluation metrics, and how to use this evaluation metrics, what we need to calculate, evaluation metrics, or maybe get rid of evaluation metric. I just don't want, what's evaluation metric? Evaluation metric is just one quantitative values to tell you is your model good or bad. Yes, it's just less evaluation metric, but sometimes, okay, I don't need evaluation metric. I just look at, okay, some parameters of my models. I look at the centroid. I visualize this centroid. Maybe in 2D graph, you can visualize it, whether the centroid is in the middle of this data point. This is, but now I will talk about the distance metric. Anyone can have a guess. What's the easiest distance metric you will use for evaluating the clustering models? This is, I think this is evaluation the most comprehensive evaluation metric I will mention today. But what's the easiest one? But thank you for bringing that goes, because silhouette is is the one you need to use in your assignment. But this is not the easiest one. I love the answer, like Euclidean distance to the center of the cluster. I really love that. This is completely your design. What's your name, Sayan? Hopefully I pronounced correct. Sayan, your answer is very great. Actually, there is a distance matrix for distortion of actually sometimes they call the Wissing cluster sum square, WWSX. This is completely the idea of your idea. You could listen to the center of cluster. This is the simplest metrics appearing in our mind, I think, for a lot of, if you think it from scratch. And Michelle, your answer is elbow. Elbow is not distance metric. Elbow is like, I have elbow is the graph. In a graph, you have, the graph have it's a line chart, right? The line has the property that it will decrease very, very fast. Then it will decrease very, very a little bit slower. So now you have elbow line, elbow like line. Elbow is like, you have this, elbow. So how you will choose the point? You will choose, elbow is for choosing hyperparameter. Remember what's hyperparameter. In K-means, the hyperparameter is number of clusters. So you use the elbow. Where is elbow? The elbow corresponding to a value of hyperparameter you will use as your as the value of your hyperparameter. Scattered plots, cluster centroids, visual view. yeah, that's true. That's true. You have, yeah. Okay, so I just go to the distortion and WWSS first. Oh, sorry, no one bring out the purity score. Actually, you should bring out the purity score for this example. Why? Because this example give you hypothesized true label, right? Idle, baby, 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 idle, idle. So what we can do? We can hypothesize this is true label. Then we have a prediction. So we have label prediction. What can we do? Accuracy, right? We just calculate the correct number of prediction, the number of prediction which are correct prediction, the number of correct prediction divided by the total number of predictions, right? This is the purity score. Actually, this is accuracy, but why we call it purity score? Anyone can tell me why we call it purity score rather than accuracy? A little hint here is like there exists a challenge to calculate this. What's challenge here? Compared to classification. I have this, then I have this prediction, then we can calculate the accuracy. But what's the challenge to calculate the accuracy here? Still 15 seconds. No answer. So I will give you the answer now. The challenge is what's the one? What's 0? 1 is one cluster, 0 is another cluster, right? That's easy. But you see, what does mean? What this cluster mean? What's this cluster refer to? Is this cluster refer to A, or is this cluster refer to B? You don't know, right? You have to make a guess. Here it's easier. It's like, okay, all this cluster, all this one cluster corresponding to the example with the label A. So I will say 1 is for A, and all the 0 correspond, all the 0 prediction, all the 0, not prediction, all the 0 cluster, all the example in 0 cluster corresponds to B examples. So I will say, okay, 0 correspond to B. Now I can calculate the accuracy, right? But before that, without knowing which cluster correspond to which label, we can't calculate that. So this is very, very easy because the prediction is completely matched. But make it a little bit challenge. How about now? You can see should 0 correspond to A, or should 0 correspond to B? Now you can see in zero cluster, we have some examples which belongs to A label, but we still have some examples in A cluster belong to B labels. Tell me your answer. Will you map the 0 to B, or will you map the 0 to A? $15 seconds. To B. Let me have a look. Oh, great. I think, can you explain to everyone how you choose B? Mitchell, can you explain to everyone how you choose B? Yeah, that's exactly how we do it when we use purity score. Everyone understand what KMeans, right? It's easy. You see here is 5 zeros for B, but only 1, 2, 3. Only 3 0 for A. So more example in cluster A with the label B compared to A. So we say 0 should map to B, right? One thing I want you to know is 0 already mapped to B. B have been mapped. Conversely, B has been mapped to 0, but B still can be mapped to 1. Okay. Here you will see for 1, we have 1, 2, 2 example with label A, and have 1, 2. Sorry, for 1 we have no example for B. But if we have more examples for label B, with label B, we can map 1 to B also. Okay, that means 0 to 1. Both of them map B. It is plausible in calculation of purity score. Let me see if you have any question. If no question, I will show how you can code this. Why I want to show you how you can code this, because it will bring out something called contingency matrix. It's not necessary in clustering, but if you see Claudican, the Claudican use a contingency matrix to calculate the purity score. You know, it's not necessary, right? Once you know the logic, you don't need to use something like contingency scores. You only need to, okay, what's the number? You just make your own, if conditional, if you use for loop, then you can loop over the maximum to find the label with the maximum number in each cluster. So you map that label to you use a for loop, right, to go over each example in the cluster, look at their label. Then you just calculate the number of the examples for each labels. Then you say, okay, I'll take this label for this class, for this cluster. You don't need to use a matrix, but when you use a matrix, it will be more efficient. It will be more efficient. But this contingency matrix is kind of similar to confusion matrix in classification. We will talk about in week 6. So it doesn't matter if you don't understand contingency matrix here, but let me do it for you. What contingency matrix does? Here, let me just give you small examples. Now we don't have too many adult and baby. We just have 5 examples. So we have A, B, B, A, here This is two cluster. We have cluster 1. In cluster 1, we only cluster one example into this cluster. Other example are grouped into cluster 2. So when you use this 2 as input to calculate the contingency matrix, you will get something like let me put it. Something like this. I already copy paste it to here to help you understand. You know what's that? This is the first row is correspond to the label A. The second is correspond to the label B. So the first column correspond to the cluster 1, second correspond to cluster 2. So when you look at the first value in first row and first column, it means this example is labeled as A, but and predicted as not predicted group in the cluster 1. You see, there is one example in cluster 1 labeled by 8. There is one example in class 2 labeled by 8. There is a 0 example in cluster 1 labeled by B. So which label will you choose? A, right? Because you have one example labeled by A, 0 example labeled by B in this cluster. So you will choose this. This is a correct prediction. How many examples are clarified in go into this cluster? So we say this is the correct prediction because we map 1 to A. And for this one, let's look at it again. In cluster 2, we have one example labeled by B. We have one example labeled by A, 3 example labeled by B. So we will map this cluster to B. Then how many correct examples in this cluster? Easy, 3, right? Because you already mapped this cluster to B. So we all only look at this number. So now how I can calculate the accuracy score, calculate the accuracy, easy. Firstly, we do mapping. Here the mapping is okay. I just use A max. This is an easy operation for matrix. We only find the maximum, for each column we find the maximum values. So these two, we find these two maximum values. Then we sum them together. Then we get the total number of correct prediction, and we sum all the values in the matrix. That will give us the total number of examples, right? Okay. So now we get the purity score is 80%, right? We have 5 examples. We have 4 of them are correctly predicted. I mean correctly predicted. It's not really correctly predicted because it's hypothesized mapping, mapping between the labels and clusters. We have 80% accuracy, 80%. 4 examples are correctly predicted. Oh, good. Okay, oh, good. This is called supervised matrix. Interesting, right? We use the supervised matrix for unsupervised models. But yeah, that's kind of a thing. But normally we don't have labels. So we need distortion and the silhouette coefficient. I don't want to talk too much because we run out of time. So like, I think someone already told you what's the distortion score. Let me copy paste here. It's from Akin. Oh no, it's from the Margaret. Let's look at what Margaret said here. How close the points are to each other with the same cluster. Let's look at how I implement it. don't look at this. Here, I just find the centroid. Centroid is every, I have a cluster of examples. Centroid is, I average each dimension of this example. So I find that point. I call it centroid because I average it. Then I calculate the distance between each data point in this cluster to and the centroid. Then I sum of them. So then I got distortion score, right? So intuitively, what is distortion score? If let me go back to visualization. Do I have visualization here? Should have a visualization somewhere. No, not yet. I want to give you an initialization, so please wait for a while. Let me find how. Okay. I just need the code for implementing the K-means. This is the implementation of K-means without using sklearn. I just do it from scratch. So let me copy paste here. Okay, so now go back. We have some graph. Let me evaluate, explain it to you. What's distortion scope? Yeah, if central is here, the distortion score for this cluster, central is here. The distortion score is compared to a central here. For this cluster, the distortion score will be much smaller, right? Because it's in the center. It's relatively close to all the data points in average, right? Compared to a central here. Then you calculate the distance between the centroid with this data point. Yeah, that is a distortion scope. Is it the same as what Margaret said? Not exactly same, but close. What Margaret said is how close the points are close to each other, What Margaret will measure is something like, okay, for this, I don't use central. I don't care about central. I will compute, this data point distance between this to this, this to this, this to this, this to this, this to this. I will calculate all the distance between any pair of data points. This is what Margaret will calculate. Actually, the idea is similar to distortion score, right? But okay, it's not quite similar, sorry. But this idea of distortion score. Okay. Now let's go to the idea of Akin. What Akin said. Akin says, well, we need to care about interdistance. We don't only care about intradistance. Intradistance is what we care about as example here. We only care about the distance within the cluster. Now we care about the distance between the data point with other clusters. Okay. So that will introduce as silhouette coefficient. This is the formula. Let me explain to you what's using the Akin's idea. Akin idea say, okay, intradistance first. Intradistance is something we care about in distortion scope. This is A. You see, what's the A? The mean distance between a data point and all other data points in the nearest clusters. Now, Margaret, this is exactly what you are talking about. You care about the distance between each pairs of data points. Now you find the answer here. But this is only care about intra-cluster distance. Akin said we want to care about inter-cluster distance. That's what B does. It calculates a data point with all the other data points in the nearest clusters. Why nearest clusters? Because we want to say in the because we want to know whether it is possible, it is more reasonable if you put this data point to another cluster, right? So that's why we care about nearest cluster, because we care about is it possible, is it reasonable to put it into another cluster? So if you put it to if you choose a very far away cluster, of course it doesn't make sense. So that's why we choose a nearest cluster. Now we have this. We have B minus A. This is just a normalization term again, so you don't need to care about too much of this. This, you know, what's the normalization? You make the number between 0 and 1. Here actually is minus 0 to 0, minus 1 to 1. Yeah. So yeah, but one thing I have to highlight is here. Highlight is, you know, distortion score smaller, better, right? But sloth score larger, better. Why? We want to enter this. We want the inter. Oh, should I say the correct thing? The larger, the better. The mean distance between. We want this intra distance to be very small, right? So then we have negative. So this should be larger. Now we want to the distance between become larger, right? So these clusters are far away from each other. So B should be larger. So B large, A small, then the total term should be larger. Okay, good, makes sense, right? Any question for the evaluation metrics? I go over this a little bit fast. Hopefully everyone can catch up with this content. Okay. I think I want to, because there are a lot of intensive things here, so I want to have some relaxed things before I go to the detail of K-means. I want to look at your past activity. It's kind of will relax you from this intensive contents. You know, you actually, if you go over my materials and you look at this things, actually it's not, it's very easy because you see here, remove some features. I don't mean you don't spend too much time on that. Actually, a lot of nuance, and no, practitioner always spend much more time than we expect. So, but I just want you to know that all these complicated concepts, I teach you these complicated concepts. Then these things is like, you just take sometimes. You don't, you won't be confused like, oh, what's this concept mean? Well, why we need to use Solow coefficient? You can have your critical thinking once you know how underlying this you know Solow coefficient, underlying the K-mean, what do this algorithm, do this metrics do? So you say, okay, I use Solow coefficient. I plot the optimal K values. Which plot I should use? Should I use the elbow plot? I think now you can make your now you can make a very logical decision now. So you will say, okay, elbow plot is not correct answer for Solow coefficient. But how about the distortion score? Distortion score is very good for choosing the optimum K value with elbow plot. So let's have a question. Anyone can tell me why I say that? Why I say for Solow coefficient you shouldn't use elbow. You shouldn't have the concept of elbow once you plot the plot the figure like you know, what's elbow plot, in elbow plot. I'll just show you an example. In elbow plot, x-axis is number of clusters you determine for K-means, and here is this evaluation matrix. Anyone can tell me why I said silhouette? Sorry, I sometimes call it silhouette score. Sometimes I call it slot score. Why the silhouette scores are not suitable for choosing elbow as the correct answer for number of clusters? Let me repeat the question. You know, what's the elbow plot? You have the number of the values of hyperparameter. Then you use this hyperparameter. Okay, I use K-mean with number of clusters specified as 2. Then I get the answer. I train the model. I get the model. I evaluate the model. I get the evaluation metric, which give me, you know, this evaluation metric is WWSS, is distortion score set like this. It's very high. Then it's become once I increase hyperparameter, which is the number of cluster. Oh, it's lower. Increase again. Oh, lower again. Increase again. Lower again. So distortion score is smaller and smaller and smaller. So we choose, but why we don't choose one give us the smallest distortion score? Because, you know, you can think about the extreme case. If you have 5 examples, you put each example as a cluster. So you have actually in this example, I have 5 examples, right? You know, 3 BB, 2 adults. So I have, so if I specify, okay, K-means, now you train on this data, which will give me 5 clusters. Actually, you don't need to train these K-mean models, right? You will know you only have 5 examples, so your centroid would be the 5 examples. So once you calculate the distance between centroid and the example in this cluster, 0. So smaller. Once the K become bigger, the distortion score become smaller. So you don't want to choose the smallest one because it's nonsense. It won't do any important thing. In machine learning, important concept called overfitting. If you choose something like here, choose something the number of clusters very big, the model will overfitting. It means your model is useless. You can't use it if you have new data. You can't say, okay, is this data belong to this cluster of that cluster? You can't. Finally, what you get is, okay, this data point close to this data point of another data point, right? So what elbow plot? How elbow plot can help us? Elbow plot says, okay, I look at the marginal rewards. You see, from 2 to 3, my rewards is very, very big. It's like from 20, 50, just go down to 50, 60 or 70. But if I increase again, it's just go from like 70 to 40. It's only like 30 reward. But here you have like more, maybe about 200 rewards. So okay, here the reward is too small, so I don't care about the increase of this number of clusters. I choose this point. This is like elbow, right? Elbow is what I showed you before. Here is elbow point. But for silhouette score, does that make sense? Does that make sense? Let me look at this. Okay, someone just gave me a silhouette score. The plot for silhouette score. Wait, let's look at this chart. Is the best number of number 5? Anyone can tell me is the best number number 5? Oh, sorry, number 4. I think you choose number 4 according to the concept of elbow. But just think again, is elbow reasonable for silhouette score? Then to answer this question, just review what I told you before. What's the silhouette score? How I calculate the silhouette score? I just go back to the silhouette scores. Anyone can tell me, is that reasonable to choose 4 as the best answer?
For the silhouette score, you choose the highest value. Is that correct?
Wait. Who said it?
Me, Mitchell.
Oh yeah, Mitchell. Yeah, very correct. You know, that makes sense, right? It's not like distortion score. You say, you know, once your is correlated to the choosing the choosing number of the choosing value of number of cluster. It doesn't closely related to that way. So you don't need to care about the overfitting. So easy. You don't need to plot. You just say, okay, which hyperparameter give me higher scores. I choose that. So here is 2. I choose 2. Okay. Okay. Let's go back to assignment. That's why I always say, okay, don't just get the high level idea. Go into the details. Know what does it mean? What's the elbow means? What's the silhouette score? Just you just step into it to take the different terms to compare the different metrics, and you figure out what's the underlying things. Why someone come up with elbow score? So you are like, okay, elbow score is not for silhouette score, it's for distortion score, something blah blah blah.
Just a question about the assignment.
Yes, please.
Should we be using scikit-learn to get the silhouette score, or should we write our own code that does it?
Be relaxed. You can use scikit-learn. You don't need to.
Oh, okay, cool.
Yeah,
okay,
yeah.
thanks.
Sorry, sometimes I just want to give you because I can code something, so you will know this is true. Otherwise, you know, once I run the code, it won't give you the good answer, so you will know it's not correct. You know,
yeah.
It's my style, so don't worry about that.
Yep. And for this particular question on the assignment, is what's like the maximum number of clusters that we should be testing? Is it enough to go from 2 to 10, or should we go beyond that?
Yeah, enough. Actually, that is another decision you want to choose. You want to make. You want to do some, you know, make some design like, okay, how many examples in my dataset? Maybe 10,000 examples. So if I have 10,000 examples, maybe I should choose 100% of examples as the number of the, you know, clusters. So yeah. So then 10 would be a good values, the up bound, right?
Cool. All right, thanks.
No worries. Yeah, you know, once you submit your assignment, I really love the logical thinking. You choose one, let's say up bound, you choose the elbow plot. You can always explain why I choose this. I will be very glad to see that. So now you can see you will, for question 3, you will use KMeans and KMeans++. So that's why I want to do the KMeans from scratch, so you will know what's different between KMeans and KMeans++. But anyone can tell me what's the difference between K-mean and K-mean plus between before I explain?
I think K-mean start with random centroid. K-means plus actually do some calculation to put logical, at least the first one random, and then the other centroid has some logic behind it.
Oh yeah. Do you know what's logic behind?
I don't remember.
Okay, now I can tell you. I can tell you what the logic behind. But yeah, I really glad you just know what K-mean plus change. You know, it's just change the initialization of centroid, nothing else. Again, I just gave you the code, so let you to have a concrete. No worries. I only expand the code line by line because that will be boring, right? I know, so I won't do that. Just relax. What I want to do is just I make a function, make each step as function, so you will see a general idea. But if you are interested in the details, you can just go into the function. So as I said before, 3 steps: initialization, assignment, update. So I make the 3 functions. Initialize centroid. How to initialize it? You give the data. You just in week 1. Actually, if you submit the assignment to me, I always like you to use, sometimes random choice or random sample. Now here we use random choice. You should know what's random choice, right? You just randomly sample the centroids. How you randomly sample the centroids? You don't like, okay, I wrote any point as a centroid. You take the example, you sample the example as a centroid. Okay, so you use the random choice. Then you have centroids. What do? You will assign the point to centroids. Just give you general idea. You have this centroid, right? You assign these points into this centroid as one cluster. So now you update this centroid. You average the x dimension in x dimension. Then you average it. You get the x position for this centroid. Then you average the y dimension for this with this data point, then you update this centroid again. Maybe it will go up a little, go left a little. So then you do it iteratively. You have new centroid, right? Then you do assignment. Again, assign this data point and update again, assignment, update, assignment, update, until your update won't give you much change, right? So these 3 steps, now I can do initialize centroid and do iteration of assignment and updates. And then what I need is, I don't need anything else. What I need is centroid. So centroid is the final parameter of this machine learning model, okay? What's the training means? In sklearn, you always call feeds, right? You call feed for K-mean, you call feed for linear regression, you call feed for logistic regression, you call feed for neural network. So it will hide all the what parameters you are updated, you are optimized. So that is not a good thing. So let's say for linear regression, what you update is W and B, right? But for these K-means, what you update is centroids. So finally, what you need is centroids. If you have centroids, you have new data, you can do prediction. You just give the centroids and then give the new data or see which centroid is close to this new data. So done. So, but what's a K-mean plus plus? Nothing changed here. Only thing changed is you rewrite this initialization function. Why we want to rewrite this initialization function, I will show you. Let me show, this is a set of data. I will initialize the centroids with K-mean, not K-mean plus plus. What can we get? You see, all the centroids are initialized here. No centroids initialized here. Why? Because you use a random choice. Random choice is like depending on the number of the its probability, right? Here you have a more number of examples. Obviously, when you do random initialization, it will more likely to be initialized with data points here. Here's just a few data points, so less likely to be initialized here. But with K-means, I rewrite this initialization function. I don't use it. Here I write the code. So let me run it. Now let me change this initialization. Let's see the result. Okay, you can see very good. It's put 1 here and put 2 here. It's scattered around. It cover all the cluster. It cover all the data points. That's what K-means++ do. Only initialization phrase. I don't have time to talk about this, but it's very interesting thing here. Yeah, you don't need to. Yeah, the high level idea is enough for your assignment. So yeah, I just ignore this content. If you're interested in that, you can go through line by line. If you have a question, you can go to my help hub session. Let me go back to your assignment. I have to ensure I give enough information for you to finish your assignment. Oh, before that, any question for that?
Yes, I have a question. Like in the data we were given, right? We could not have a true value, true labels. Is it correct? Because we
Which data you mean the assignment in past?
the past task week 3, I think.
Oh yeah. You don't have a label.
Yeah,
yes,
we don't have a label. Yeah, correct.
Yes.
So like the only does that mean that the only evaluation choice that we have is the Hote or the one that you just mentioned, you just taught us, WWSS, the distortion one? There's only 2. We couldn't do like we couldn't do parity and others, right?
Yeah, you can do distortion. Distortion is WWSS, and you can do silhouette, but you can't do purity.
Okay, thank you. Because the reason was because we wouldn't have the ground truth, right? The ground truth. Okay, thank you. Understood now. Thank you.
No worries. Yep. And for this Q3, I think you have enough idea of what's K-means and K-means++, but it still doesn't help you to to relate to your explanation to the details of K-means. That's why I don't give you the too much detail of how. Actually, I want to give you details of how K-means plus initialization phrase work, but it doesn't help you here because this data sets, if you use the sets, then run K-means and K-means++, the result will be similar. So when you compare your result, you don't need to give me too much detail. You can say, okay, it's similar, it's a little bit better, or something like that. It's enough. One thing I need is just say something, but I don't expect some, complex things. And for first question is say, okay, run 15 times. Just same thing here. Just do the work. And you plan something. Always K-means++, because of the initialization of centroids, which are far, is just apart from each other. So, it's always become better. But if you run it many more times, but if you only run it once, maybe not many because the initialization phrase is random. Sometimes because of this randomness, the difference is not too big. Sometimes even K-means will it will perform better than KMeans++ because of this randomness. But if you run it 15 times or maybe 500 times, this randomness can be overcome. So that's why they let you to run it 50 times.